Alright, so today we're doing Keeper 2.2 normal distributions. Alright, so basically a normal distribution is simply a density curve. It's a density curve that we use quite frequently because it represents any of our distributions that are normal. Alright, your normal curve, again, looks just like a density curve. The only thing is it's symmetric, it has one peak, and it's bell-shaped. All right, in order to properly draw your normal curve for your normal distribution, you want to make sure you include the mean and the standard deviation on each one. So like here we included the mean and we included the standard deviation. We have one standard deviation away, and then we can go two standard deviations and so on and so forth. All right, so every time you draw your normal curve, you want to make sure you actually include the mean and the standard deviation. All right, so this just basically sums it all up. Our normal curve, our normal distribution has a normal density curve, and that density curve is symmetric, and therefore the mean is at the center. All right, it's not skewed left or right, so the mean is dead center. And then the standard deviation is the distance from the center to the curvation point on either side. So you can go like a positive standard deviation, or you can go a negative standard deviation away. Now, the abbreviation that we use for a normal distribution is this N apostrophe mu comma sigma. So this is the mean, and this is your standard deviation. Notice that this is not the normal abbreviations that we use for mean and standard deviation, and that's because these abbreviations are for population. So let me just write that in here, and don't laugh at my handwriting. Alright, so again, when I do this, I'm normally talking about the population. I'm not talking about a sample, so I wouldn't use x bar and s of x. I'm using mu and sigma for my abbreviations. Alright, so again, we use this normal distribution to show, what our real life data is, like IQ scores, SAT scores, stuff like that will be approximately normal because it's symmetric. So we use these things all the time, and that's why it's very, very important, very huge in this class. Alright, so we have something called the empirical rule, the 689599.7 rule. I'm sure you guys probably heard this before, but basically what it's saying is that approximately 68% of your observations fall within one standard deviation of the mean, 95% of your observations fall within two standard deviations of the mean, and 99.7% of your observations fall within three standard deviations of the mean. So you see down here we have 68% is one standard deviation. That means this whole like whitish grayish area is 68%, and then 95% falls from here to here. So this whitish gray area plus this light blue or light green, and then the rest of it, so your 99.7 falls from three standard deviations plus or minus three of the mean. So that's about 99.7% of your data. Now, some of you guys probably learned it a little differently, because I definitely learned it differently. Now, I learned the rule because the rule is helpful, but I also learned actually breaking it up. So like, let's say this was my normal curve. Boy, that's bad. All right, let's erase that. That's ugly. Let me use the one that they have, just so you guys can see what I'm talking about. But essentially what I learned was that this out here was 0.15. This in here was 2.35. This was 13.5. And then if we cut this down the middle, I knew that this was 34. And the same goes for the other side. So like this would be 34. This would be 13.5. This would be 2.35. And this is 0.15. So I definitely encourage you guys to learn it both ways, with the empirical rule and the individual percents, because both of them will help in solving problems. Like sometimes the empirical rule will be better, and sometimes actual percents for the individual standard deviations would be better. All right, so here's an example. We have the distribution of Iowa test scores for 7th grade students in Gary, Indiana. The distribution is normal, so they told us it's normal. We can't ever assume that it's normal. They need to somehow tell us. And they're telling us that our mean is 6.84 and our standard deviation is 1.55. All right, so the first thing they want us to do is sketch the normal curve, the normal density curve. And that's really easy. We know it's just a symmetric bell-shaped curve. The key is that you have to make sure that you actually put in your mean as the middle number and then add 1.55 to the mean to get the next number. So if I did like 6.84 plus 1.55, I would get the 8.39. Or if I did 6.84 minus the 1.55, I would get the 1.29. And I keep subtracting, or I keep adding the 1.55 each time to actually get my curve drawn out. Once I get that curve drawn out, I can figure out different percents and different probabilities. So it says, what percent of the ITBS vocabulary scores are less than 3.74? Well, with my numbers, I see that here's 3.74, this line. Make sure you understand I'm talking about this line right here. And I want everything that's less than that 3.74. All right. So essentially what they did, well, they said, well, I know 95 is, 2 standard deviations away. That leaves me 5 on either side. So 5 together. And then if I divide that by 2, that will give me the 2.5 in that left tail. The way I personally did it, because again, I learned it 2 different ways. I knew that this was 0.15. And I knew that this was 2.35. Or if I add those together, I get 2.5. So again, you can do it either way you want to do it. Doesn't really matter to me as long as you understand what you're doing. All right, so the next one says, what percent of the scores are between 5.29 and 9.94? So again, here is your 5.29. Here's your 9.4. Again, we're talking about these lines as your 5.29 and your 9.94. Again, we're using the empirical rule. Well, they use the empirical rule to say, okay, this is 68. This red section is 68. Plus, I know, well, if I take the remainder that's left over, our 95% rule minus the 68% divided by 2, I get 13.5. So I know this is 13.5. And then if I just simply add those together, I would get my answer. All right. So again, that's one way of doing it. I just simply took what I already knew. I knew this was 34. I knew this was 34. I knew this was 13.5. And I added them all up together. All right. So what's really, really nice about your normal distribution is that you can standardize these values. We can use our z-scores that we learned in Keeper 2.1 to standardize the values. Now on your worksheet, the homework worksheet 2, it said quiz 2.1a or something like that. It asks you to standardize the mean and the standard deviation. That very last question a lot of you guys asked me about. Well, what's nice about that is when we standardize the mean and standard deviation of something that's normal, our mean and our standard deviation will always be 0 and 1 no matter what. All right, so if we're standardizing a mean and a standard deviation, we're making it standard, we're making it such that the mean is 0 and the standard deviation is 1. Therefore, any normal distribution that's standardized with our z-scores, these are z-scores down here, the middle number would be 0, and then I'd increase 1 standard deviation each time as I go out. This is what your standard normal distribution is, standardized values. That means it's z-score values, and this is what it will look like. All right, so what's really nice about our standard normal distribution is that all the probabilities are going to be the same under the curve because it's standardized. Everything has a mean of 0 and a standard deviation of 1. So everything's going to be the same. Therefore, we can have a table to actually figure out our percents and our probabilities under the curve. All right, so in the back of your book, there's a table that says Table A. All right, it's on, I don't know, it's one of the tables. It's like the first table in the back of your book. And it was also on the slow test. There was an additional pack that I passed out with reference tables. It's the very first table, and I'll show you guys again in class. But table A basically is a table that you'll use to find your standardized values. So basically what it's saying is if you have a z-score, you can use this table to figure out the different probabilities. One thing that you need to note, like really, I'll probably underline it or highlight it in my notes, is that table A gives you the probability or the area to the left of your z-score. All right, so it's telling you everything that's to the left. In other words, if you wanted something that was greater than your z-score, you want to get the answer straight out. You'd actually have to do 1 minus the answer that you find in your table. But if it says less than, like what's the area less than whatever, well then you can just use the table outright. You don't have to do anything funky. Alright, so for this example, we're looking for the probability that z is less than 0.81. So again, because it's less than, I can go straight to the table and use the table without doing any type of other calculations. Alright, so z is less than 0.81. The first thing I'm going to do is I'm going to find the 0.8 along the side, and along the top I'm going to find the 0.1, the 0.01. So if I add those together, basically 0.8, 0.01, I'll get 0.81. Alright, and what I'm going to do is I'm going to find the intersection between that row and that column that I'm looking for. So here's my 0.8 row, and here's my 0.01 column. The intersection is right here at this 0.7910. In other words, how much area is under the curve from that's less than 0.81? Well, 0.7910. All right, would be my answer. All right, so again, if I drew it out, here's my 0.81 on the curve. I want to know everything that's less than it. Well, it makes sense that it's a fairly big number, greater than 50%, definitely, because it's beyond the halfway mark. So 0.7910 would be my final answer. All right, so here's another example. It says find the proportion of observations from the standard normal distribution that are between negative 1.25 and 0.81. All right, so here's the area to the left of 0.81. All right, and I use the table to get that area as 0.7910. And then I also found the area to the left of negative 1.25. So I used that table and I found that is 0.1056. Now basically what's happening is I want the area between the two. In other words, I want the area from here to here. So if I found all of this and I took off the little tail, subtracted off the little tail, I'd be left with what's in the middle. So if I take the 0.7910 minus the 0.1056, I get my final answer of 0.6854, which is the intersection of those two. In other words, that's telling me the proportion of observations or the probability that our observations will be between negative 1.25 and 0.81. All right, and again, you could do this differently. I use the left area because the table flat out gives me the left area, but I also could have done the same thing with the right area. You just have to remember if you're doing the right area, then you have to subtract 1 from whatever you find in the table. All right, so you see here we did 1 minus the answer. All right, so if we're solving problems involving normal distributions, really simple. First, you want to express the problem in terms of whatever variable you're trying to look for or assess. Next, you want to try to draw a picture because a picture will help you make sense of the problem. You don't necessarily need it once you get really good at it, but it's useful because if you get a crazy answer, you get an answer that doesn't make sense based on your picture, you know you jacked something up. Then you want to do your calculations, do your z-scores, whatever you need to do. So we're going to standardize it, get our z-scores. We'll use our table A to get our actual percents and our probabilities. And then lastly, you want to conclude in context. All right, make sure you're doing it in context. Don't just say the z-score, blah, blah, blah. You want to say it in context to whatever the problem is. All right, so here's another example. We have Tiger Woods, and we're looking at the distance the ball can travel. And we're saying that this is normally distributed with a mean of 304 and a standard deviation of 8. So it says, what percent of Tiger's drives travel between 305 and 325 yards? All right, so the first thing I'm going to do, I'm going to figure out, okay, my x is my distance. That's what I'm trying to figure out. I'm looking for the distance that the ball travels. So x is distance. And when I draw my picture, again, my mean goes directly in the middle. Count out my standard deviation, so I'm adding 8 each time. I'm subtracting 8 each time. Then I identify where 305 is. It's right after the mean. And then 325 is right out there close to the tail. Now notice here that the 305 and the 325 are not directly on the lines. So I can't use my empirical rule. I can't use my, 0.15, 2.35. I can't use that because they're not falling exactly on the line. I have to use z-scores in this case because otherwise I wouldn't be able to find out the answer. So the first thing I'm going to do is I'm actually going to standardize these values by finding the z-score. Remember, your z-score formula is x minus x bar over your standard deviation. So I get 0.13 for my first standardized value. And then when I standardize the 325, I get 2.63. Once I get those two things standardized, basically what I'm going to do is I'm going to recreate my drawing, but I'm going to do it with my standardized values on my horizontal. Alright, so once I get that, again, just like the last problem, I'm going to figure out what's the area to the left of the 2.63. So I want to know this whole green area. I'm going to subtract that from the area to the left of 0.13. When I subtract those, what's left over is going to be my answer between the 0.13 and the 2.63. Alright, so the area to the left of 2.63 is 0.9957, and the area to the left of 0.13 is 0.5571. When I subtract those two, I get 0.4440, which tells me that about 44% of Tiger's drives will travel between 305 and 325 yards. Alright, now let me go back 1 second. Remember, this only works if your stuff is normal. If your stuff is not normal, well, it's not, you can't say that. I can't say that with certainty. I can only say that I'm pretty sure that it's going to, 44% of his balls are going to travel that distance because the distribution was normal, because it was symmetric. Alright, so again, whenever we're trying to assess something to see if something is normal, because again, a lot of problems won't specifically say it's normal, right? A lot of times you might be given a data set and you have to determine yourself whether it's normal. So the first thing I would want to do is plot my data. I want to see if it looks roughly symmetric, if it looks bell-shaped. Now that's not enough to say that it's normal. That's just giving me an idea. If it looks roughly symmetric, I would keep going with the process. If it's clearly skewed, I probably stop and not even keep going. I would just say it's not normal because it's skewed. But the second that I think is roughly symmetric, I'm going to keep going with my process. I'm going to check whether the data follows the 68, 95, 99.7 rule by counting the observations that fall within 1, 2, and 3 standard deviations from the mean. All right, so again, I would just add up all my values, see how many fall within 1 out of the total. If that's 68%, then I feel pretty good. If I count them all up and it's not close to 68%, then I'm going to feel pretty unhappy with my data set. All right, another thing that we have is software that will also tell us whether or not a data set is normal. We can use our graphing calculators or any statistical software to see whether or not something is normal. The way we do that is we create a normal probability plot. And your normal probability plot basically just shows you whether or not your data set is normal. So in your normal probability plot, what you're looking for is you're looking for a straight line. If you have a straight line, then you know it's normal. If it's not a straight line, then it's probably skewed. So for instance, this histogram that I have over here is clearly skewed, right? If I do a density curve over it, it's clearly skewed to the right. So I would not expect my normal probability to plot to be a straight line because I know it's skewed. And sure enough, when we look at our normal probability plot, we have this curvation in it, which tells us that, hey, this thing is skewed. Not only that, because it's curved down like this, almost like a hook or C, because it's curved like this, I know that it's skewed right. Alright, so I really didn't need to see the histogram at all. The fact that this thing was curved downwards tells me it was skewed right. If it was curved like this, then that would be skewed left. Alright, so it just depends on the curve of it. And that's important for an AP exam. So again, let me do it up here. This is right skewed, and this would be left skewed. Alright, let me write that in. So this is right skewed, and this is left skewed. And then again, if it was straight, something like that, that's normal or symmetric. So again, we know that this thing, this histogram, this data set was going to be skewed right. All right, that's it.